Hello, and welcome to our talk today about the industrial Internet of Things and how to simplify your process integration. My name is Andrew Wilson. I'm the Product Marketing Manager here at MKS Instruments in the Automation and Controls Solutions business unit. Our agenda today will be to discuss the smart factory motivations. We will be talking about the differences between the background protocols of TCP and UDP and how they're supported in the Industrial Internet of Things protocols. And then the actual protocol summary that we studied will be presented for AMQP, CoApp, MQTT, DDS, and a little summary conclusion of these investigations. And we'd like to share a small research, real-world case study that we've worked on. So next, diving right into it, let's talk about smart factory, Industry 4.0, and industrial internet. So really the motivation behind smart factory is to do more with your data, right? We have so many sensors, we have so many gauges, everything is feeding data. We want to be able to capture that data and understand what's happening on our process and control it. So as you can see here, the hindsight aspect, are you actually able to capture an event that is not desirable? Do you have your customers telling you about your problems before you find them? Next would be the insight tier. Are you able to identify what a root cause to what happened on your machine? Do you have, how much value can you find in your data? Next is, can you actually understand when you have problems? And that way you may be able to even remove the product from shipping to a customer or making it to an assembly next phase. That way, you're not able to send those bad parts to your customer or ship that material. And then lastly, can you actually do closed loop control so that you can actually force the machine to behave in a certain way if there is a deviation that's controllable within the machine or process. So these are the things that really are the motivation for the smart factory. As far as the pillars of enabling smart factory, they typically fall into these four categories. Some sort of IoT gateway where you're converging and converting all of the sensors on the machine into one field bus, into one IoT protocol, and that way you can manage that data. You can send it for analysis. Secondly would be the connectivity. What protocol are you going to be using? Is it a DDS that you're going to be sending to the server level? It needs to be, most importantly, secure. It needs to be scalable. You will likely either grow your install base of machines, your factories, multiple factories. It needs to be scalable in that regard. Next, it needs to be typically high performance. There's a massive amount of data that's being generated, and you're really needing to not peak out and extend the level of your CPU or your servers. Number three would be the analytics. What is it that you want to do with your data? It's not enough to just capture the data, but you really need to make educated decisions from your valuable data that you're collecting. Your edge computer will be able to generate applications and run software so that you can make these educated and actionable decisions. And lastly, some sort of dashboard, a visualization. These applications can take all of this consolidated, condensed data from multiple data sensors and provide insights into an event that you can take. Now it's difficult, right? All of the sensors that you're going to be purchasing, all of the softwares, they're not going to be the same they're not going to be the same protocols. Not everybody's going to be at the latest generation. They're not going to have the protocols that you need. There are so many different protocols out here. This is just a few. So how do you choose one to work with? This is just at the machine level. Next, if we looked at the factory level, there's all sorts of different field buses. There's protocols. There's SEX, GEM, EDA, Interface A, your own internal proprietary. This, I wouldn't say this further complicates things, but it doesn't make it easier. And you have everything running into your management system, your fault detection, or your SQLite database, or your data storage, your servers. It's tough to choose. It's tough to choose one. What does that mean? What tools can we use to consolidate all of this data, to easily pass this data directly from the sensor all the way to the factory level? The machines themselves are solving complex problems. Managing the data, managing the information. It should be easy. It should be easy. And one way to do that is to use an IoT protocol, an IIoT protocol. But now we need to decide which ones to use. So let's, these are some of the emerging protocols that we're going to present here today. It's not all of them, but it's some of the leading ones. And so let's kind of dive right in. On the backbone of the IoT protocols, they're basically written in either TCP format or UDP format. So let's look at the difference between those two. It's really the TCP and UDP. They are really determine how the data is managed and exchanged over the internet. So it's built on top of the Ethernet IP protocols. And if you think of our new world that we live in with virtual webinars and virtual meetings or remote working, everyone's saying we have streaming video and streaming this and streaming that. Even though your data is streaming, it's still being broken up into little chunks of data called packets. And these packets are streaming over the internet, from one location to another location, from your PC through a server. And so you're seeing this video today, even though it's streaming, we are sending that data in little packets. So for the TPC side, these actually the packets get broken down and shipped through the internet, over the internet, and once they arrive at their destination, they get reassembled back into the right order that they were shipped. So there's an order that they're sent, and they get reassembled once they get there. Now, not all packets arrive at the same time, because these networks are managed. There's a priority. Not everything arrives at the same time. So TCP protocol will reorganize these in the same manner that they were sent. So there's a little bit of overhead, processing overhead, some latency that's associated with that. However, everything gets put back in the right order, so there's no data corruption. At the same time, there's actually a handshake that goes on in the TCP protocol. So the packet that is sent, the recipient will actually send an acknowledgement back and say, yes, I've got this packet, send the next one. Now, on the other hand, TCP, it's a little bit faster, it's a little bit more simpler. The UDP does not need to acknowledge the recipient packet has been received. Now that's great because it's faster, there's less overhead, less processing, but that means that some packets get lost. And so while computers can communicate more quickly, your data might be a little bit corrupt. So a little bit of a summary here. TCP is most commonly used these days. It's reliable, it ensures the delivery, so there's no packet loss. It's a little bit slower, and we're talking microseconds, milliseconds here. It's a little bit slower, but it does consume the bandwidth. But it's important for things that require things without corruption. So file download, email, those kinds of things. UDP, very fast, but you have a little bit of packet loss, which has some corruption integrity with the files, but it does require a few resources. It's very fast. So target applications, gaming, voice over IP. Okay, great. We've got that covered. Let's move on to the first protocol studied here, AMQP. So this is an application layer protocol, and it's really meant to be message oriented, and it's designed for middleware environments. This protocol consists of 3 components. So let's take a look at each of those. The exchange. So this is a device, a broker. It's a thing. It's a server. Now this exchange will actually receive the messages from a publisher. What is a publisher? So a publisher is a sensor. It's a gauge. It's something that you're receiving data from. So this sensor is publishing data to the exchange, and this exchange will route them into separate queues. And the queue is just the line here. So the queue will actually store the message, store the data until it can actually be processed by the client's software that's consuming that particular message queue. And then the binding component is more about quality of service, priority, data type, these kinds of things, security levels, these things. Next, so let's take a look at this a little bit visually. So we have the publisher on the left-hand side, where these are the sensors that are pushing the data into the broker. We have, so the broker is a thing, it's a server. And the exchange will actually take all that published data, and it will say, all right, I know that the subscriber needs these types of data in its subscription to the data. It will actually marshal that data, create a data set, and then the subscriber can pull that message queue. So let's look at quality of service that we mentioned. In AMQP, there's 3 tiers, 3 levels. So the first one, at most once. So this will actually send it one time, and it won't check that it was received. It won't check that it got there, and it's not going to send it again. The next higher level of quality of service, it guarantees delivery, but it also may receive duplicates. So if you're on the subscription side, if you're a subscriber, your software needs to handle duplicate receiving packets. And at the same time, exactly once, so your publisher, your broker may send this data multiple times, but it's guaranteed to be only received once. Now, at the same time, top to bottom, we have some processing overhead from low to high. So in doing so, while you are guaranteed to receive a data packet only once, your processing overhead and your latency is a little bit higher. All right, so let's look at a little bit of a summary for AMQP. It's good for reliability. It's very fast to implement, easy to maintain, not a lot of levels. However, on the challenges side, there's still a broker, there's still a thing that's doing all of the marshaling of the data, and it's considered a single point of failure, SPOF. And the server is considered a bottleneck. So it's not so scalable in that regard, and the data is not in real time. Next, let's look at CoApp. Now, CoApp is, it's a protocol that's it's really a utility protocol, and it's really meant to handle rather low-level, simple devices like power sensors, switches, valves, things that don't have complex smart data, at least smart gadgets. It's also built on the UDP protocol, light implementation, which makes it fast but a little bit unreliable. So as you can see in the cartoon here, there's actually a CoApp server as well as a REST proxy for this protocol, and which makes it a single point of failure that's actually doing the protocol, and it's really meant to bridge the gap between a constrained network and kind of an outside internet-based protocol. So CoApp, it's simple, low overhead, easy to implement. Synchronous communication is not necessary. It does acknowledge the messages, so it does make it reliable. But at the same time, it has pretty poor quality of service. The packet delivery rate and the order at which the packets are received are pretty poor. And the security is very poor because of the lack of encryption. Great. Next, MQTT. Now this is we're starting to move into some more advanced protocols. They're a little bit newer protocols. They have a little bit more built-in qualities to them. Now, the MQTT, it's actually a broker reliant publish-subscribe message protocol, and that's really great because it's built on TCP, so it's more secure, it's more reliable, and it has a little bit more security built in. It's built for centralized data collection and analysis, as opposed to something that is decentralized, like DDS that we'll talk about. So that's good. So actually, let's look at the kind of the cartoon here. So the publisher is your sensor, but it's not going to publish all of its data. It's going to say you set up what's called a topic, and the publisher will say, I am a temperature, and I am a power, I am a pressure. So it's going to push all of this data to the broker, and that topic is going to just reside on the broker. And it's not going to necessarily, the broker's not going to look at the data coming in. It's not going to marshal any of the data, where it will say, I know the subscriber is going to need this, and it's going to order everything in line. In MQTT, the subscriber will actually subscribe, or I've heard this to say that it actually just pull what it needs, right? So you can see subscriber 1 is going to pull temperature from publisher 1, and subscriber 2 is going to pull power from publisher 3. So it only gets what it needs, and it doesn't rely on the broker to actually do all of the data organization and structure for it. So it makes it a little bit faster, a little bit easier than the first one that we talked about. So MQTT is still a client-server model, where the sensor is the client and your publisher is the server, and you're actually going to be pulling that data in discrete chunks, and that data is actually opaque to the broker, so the broker is not going to be doing any of the processing. So the overhead is rather low for the broker, and that's great, but there is still a broker, which makes it a single point of failure. And the clients can subscribe to multiple things at once. It's not just one thing at a time, one topic at a time. Great. So we're going to look at the quality of service for MQTT, and it's very similar to the others, where while MQTT calls it fire and forget, acknowledged delivery, and assured delivery, it's the same tier structure. Where and I've put here kind of the similar names that we've used previously. So for number 1, fire and forget, the data is sent once and only once, and we hope that the broker picks it up into the topic and the subscriber can get that data. Acknowledged delivery, messages are retried until you get an acknowledgement from the receiver, from the recipient, from that subscriber and the broker that say, yes, I've got it. Assured delivery, there's a two-way handshake that says, yes, I've acknowledged that I've received one copy and only one copy of the message that's being sent. So benefits, drawbacks for MQTT. It's good for simple packet payload. It is expandable. It's light on bandwidth. It operates over TCP, and it's a good it's a very good consumer protocol where you're doing mobile apps and machine-to-machine scenarios, and there's good good power consumption in the favor of this. So, but on the challenges side, there still is a broker. There's still a single point of failure. Now, on the security side, there's not too much built in for MQTT, so that would fall on the user or the customer to build in those additional security layers on top of MQTT. And one thing that's important for more advanced applications is the real-time bit. Having a distributed clock where everything runs on the same timing, it can be very important. So next and lastly, let's talk about DDS. So DDS is Data Distribution Service. Now, it's one of the newer protocols. The specs for this protocol came out of the Department of Defense, where you are actually needing all of the data to be available everywhere at the same time. And what that does is it allows a decentralized IT infrastructure to be able to manage all the devices, all the applications, all the data, all at the same time, in all locations. Now it's very reliable, it's expandable, it's real time, and it supports large data sets at very high performance. It's a more software-based program, so it's very scalable. And one of the biggest advantages for DDS is that there's no broker. There's not a thing. There's not a server doing all of the data marshaling, of all the controlling, which really means it's peer-to-peer. So the things that are producing the data are connecting exactly with the things that consume the data. So what does that really look like? So previously we had in the middle, we had a broker, a thing, a server actually doing the data. Now, while this image here, we have a cloud drawn for what we consider the DDS domain, it's not really like in the cloud. It's not like Azure or AWS or something of this nature, where there's something in a server farm processing all the data. The domain is just the space where all the data lives. So the DDS. So if you're a publisher of data, you actually publish it to the DDS domain, and there's nothing marshaling the data, and you're actually able to, as a subscriber, pull that data from the domain. And within the domain, there are structures for quality of service, for data types, topics, formats, and these things. Each publisher has its own quality of service, as well as the subscriber has its own quality of service. So you can set that up. It's very configurable in that manner, and it does show some benefit, because if that in the other examples, if the broker does go down, hard down, your data is not lost. Your data, you're still able to control, you're still able to communicate, you're still able to receive the data. So inside the DDS protocol, the DDS protocol is based on UDP. Now you think to yourself, well, that's unreliable. It's fast, but it's unreliable. There's packet loss. And what happens is DDS actually handles all of those chores that are, you might say, lacking, right? That might be a negative for the UDP. So all the flow control, the retries, the security, DDS handles all of those things inside the protocol. So it's fast, and the protocol handles those things. And really, one thing to note is that any node can be on the network can be both a publisher and subscriber. So if you're a sensor and you're pushing data to the domain, you can also subscribe to something on the domain. So it's a two-way street. So in other protocols, it's just a one-way street. So kind of the key benefits. There's a little design time that's needed to handle the data and the interactions with the subscriber. Now, as you can see here, there's 23 levels of QoS, quality of service levels, within DDS, which is much higher than many of the others. And the DDS, seamlessly and transparently handles all the message delivery without intervention with the user applications. So you can actually, the sensors and publishers can actually self-identify on the network. And as a user, you don't need to write code for new sensors and when you're expanding your network to actually identify those components. So let's look at kind of the summary of DDS. It's a decentralized network, so there's no single point of failure. Very scalable. It's software-based protocol, so it's easy to expand. You have distributed processing across the network. There's no one server. The data rates are very high. It's very high performance. The latency is very good, very low. And it's designed for real-time or near real-time networks. Now the challenge is it's a little bit more difficult to implement because it's software, but it uses UDP to avoid those large number of connections that are required. So some of the best applications for DDS, they're some of the more advanced applications, aerospace, defense, autonomous vehicles, robotics, motion control, transportation. It's really anything that has mission critical type applications and that require real-time data exchange. So in quick conclusion here, I think this table would accurately represent what might be considered the best protocol for process-like industries, because of the real-time and security features and the scalability. I find DDS to be one of the better components. MQTT is still good, but it does carry that broker still, the single point of failure. So let's look at a real-world case very quickly. You have up here on your the top right-hand corner some sort of process equipment, and you're actually have multiple sensors on the tool showing and using different field buses, EtherCAT, DeviceNet, serial, anything you can throw out there. So in this architecture, you can see there is a controller here. What the controller does is it does all these things here. You can actually configure the devices on the network. You can actually configure the network itself. It acts as a field bus gateway. You can perform some analytics and diagnostics all on one device. And in doing so, you can send that data off to your next higher level, or your MES, your data aggregation, your servers. But let's look at some performance. In the real world, using one slave device in the EtherCAT protocol, being able to convert the EtherCAT data, and we're using this DDS gateway here. So one side of the industrial PC is handling all of the reading and writing of the EtherCAT data, and it acts as a master to those devices. The other side of this server on this industrial PC is the DDS gateway. So you're actually taking that EtherCAT data and publishing it to the DDS protocol into that domain where you have the subscribers reading that data in a DDS format. Now, if you're taking this data size based on the setup of the file system, you're actually able to publish in about 300 to 500 microseconds. Now this is on the network. This is not just within the server itself. So it's pretty quick, very fast. Now, if you're just looking at one EtherCAT slave from publishing EtherCAT to EtherCAT, the requirement for this is really based on an EtherCAT limitation rather than a DDS or a server level component. So you're able to achieve, very large data sizes, and you're able to move them very fast. And this is, for, moving the DDS protocol, and you can do that within the single EtherCAT frame. So that is the conclusion of our talk today. I wanted to thank you very much for attending. If you have any further questions, please feel free to reach out to me over email or the phone provided here. I appreciate your time. Thank you very much.